in chapter 10, which will be our last chapter. So 8.2 was just the introduction to hypothesis tests. 8.3, that was hypothesis tests about a proportion. And so 8.4 is on hypothesis tests about a mean. So it says, as we saw in chapter 7, if the population standard deviation is unknown, our only option is to use the sample standard deviation. And since the sample standard deviation is itself a random variable, because we'll generally get a different standard deviation for each sample, then the shape of the distribution is no longer exactly like the normal curve. It looks a lot like the normal curve. It's bell-shaped. It's different in the tails. And so we have to use this other distribution called the t distribution. The steps followed for conducting hypothesis tests are basically the same as they were when we were doing tests for a proportion. And then when we did confidence intervals, if we did know the population standard deviation, then we could use the normal distribution and z-scores. Otherwise, then we have to use the t distribution and t-scores. I am going to show you, well, on the next page, that our calculator will really do most of this for us. I've kind of made us do it, well, sort of by hand, but sort of with technology up to this point. But we'll see today that our calculator will actually do most of the work for us. So these first couple of claims, all we're doing is saying whether we're going to use the normal distribution, the t distribution, or neither. We're not going to do the test, we're just going to say which applies. So the first one is about FICO credit scores of adults. So this, the mu equals 678, that would be our like null hypothesis. And then for our sample data, n is 12, the sample average is 719, the sample standard deviation is 92, and the sample data appear to come from a population with a distribution that is not normal and sigma is unknown. So for this one, these are the same criteria we had for confidence intervals. Should we use the normal distribution, the t distribution, or neither? Okay, so the fact that it's not normal is only important sometimes. When is it important? Right. If our sample size is less than 30, then that's a big concern. If our sample size was 50, we don't care that it's not normal, because then the distribution of sample averages is still normal. So our n is less than 30, and the original data is not normal, so neither applies. We can't do anything. Now in the next one, our n is bigger than 30, so automatically it's either going to be normal or t distribution. Okay, so here they give us the alternative hypothesis, mu is less than 0.2. Okay, so there were 52 things in our sample. The sample average was 0.1, the sample standard deviation was 0.26. The sample data appeared to come from a population with a distribution that is very far from normal. This part, we don't care since n is greater than 30. And sigma is known. So would we use the normal or the t distribution then? Normal. The fact that sigma is known means that we're going to use the normal. Okay, so here it says find the p-value. So it's a two-tailed test with n equals 15 and test statistic t equals 1.495. So if our test statistic is a t-value, then we know we're using the t distribution. And it's a two-tailed test. And our test statistic is 1.495. So with the p-value approach, we use the test statistic to start our tails. So I'd have 1 here at 1.495, and then because of symmetry, this is negative 1.495. Remember, the P in p-value stands for probability. So and I know I'm using the t distribution. So there are there are actually 3 things on my calculator that have the t on there. The INVT, the TPDF, and the TCDF. And just like with the normal, we never use the PDF. So would we be using, to find probability, would we be using INVT or TCDF? TCDF. And then it doesn't matter which tail you use. I like to keep my numbers positive, so I'm going to use the upper tail. So what would my lower be? 1.495. And then what would my upper be? 1E99. And then remember, with the t distribution, we have to do degrees of freedom. So what would degrees of freedom be? 14. And then when I do that, when I'm done with that, then I'm going to multiply my answer by 2 because I have 2 tails. This will find the area in this tail, and then I want the area in both. So I get 0.1571 about. Well, this one, the next problem says test the claim, but they don't give us a level of significance, so we can't really state a conclusion unless they give us a level of significance, but we're just going to find the p-value. So this time it's a left-tailed test, so I only have 1 tail. My test statistic is negative 3.518. And they tell us it's a T again, so I'm going to be using TCDF. What would my lower be this time? Negative 1E99. And then my upper? Negative 3.518, and then what about degrees of freedom? 10. And this time we're not multiplying by 2 because it's just a one-tailed test. So I get 0.0028. So whatever we had, there's less than a 1% chance of that happening. So it would probably, regardless of the level of significance, you generally don't set it to be less than 1%. There might be some circumstances where you do. Okay. So it says we can use our calculator to perform almost every step of a confidence, or I should say hypothesis test for us. The one thing our calculator won't automatically give us is the critical value. It will give us the test statistic and the p-value. So it says the printout looks like the image shown below. In that printout, identify the null and alternative hypotheses, the test statistic, the p-value, or the range of p-values. Okay, so when they say null and alternative hypothesis, from the printout, here, since it has a less than, that must be the alternative, right? Because the null hypothesis always has to have a what sign? Equals sign, right? So it must be the alternative is that the average is less than 24, the mu is equal to 24. So there's the null and alternative. The test statistic, that is just the very next line. So that right there is the test statistic. The p-value is the next one. So the p-value, remember, is the probability of getting the results we got if the null were true. So with this e negative 9, that would mean there's almost a 0% chance. Okay, so let's do an example. Okay. So it says a national program called Girls on the Run. Has anybody here heard of Girls on the Run? No. Okay, so it's a great program. I was a volunteer coach for a few years. So they always need coaches, and you don't have to be a runner. You just have to want to help 3rd, 4th, and 5th grade girls build self-esteem. So it's at a lot of different schools in the metro. Anyway, so it is sort of about running, but it really is more about building self-esteem, character, helping girls make good choices, and learning how to be a good teammate. So March 2015, I should say study, by Maureen Weiss from U there, measured pre- and post-season survey responses from participants. One of the categories in the survey was confidence. So there were 1,481 girls who indicated low levels of confidence at the beginning of the season. So they gave answers on a scale of 1 to 5, 1 with low, 5 with high. The mean score at the preseason was 2.31 with a standard deviation of 1.2. On the postseason survey, those girls had a mean score of 2.58. So it says, test the researchers claim that the Girls on the Run program helped boost confidence for girls who originally lacked confidence at the 0.03 level of significance. Okay, so when we start out with a hypothesis test, we should always state what our hypotheses are. Okay. And so our symbol after H0 and H1, the only things we're doing tests about in this class are proportion and mean. And so what symbol would I put here? A P or a mu? Mu, because they talk about a mean score. And for the null hypothesis, it's equals. And for the alternative, we choose from less than, greater than, not equal. So what do you think our mu would be for the null hypothesis? $2.31, right? Because we're going to assume that the Girls on the Run program doesn't have anything to do with it, okay? So it should be the same after as it was before. So 2.31. So I know I need a 2.31 also in the alternative, and then what symbol should I put in between? Less than, greater than, not equal? Greater, because it says boost, so that would mean higher confidence level. So when we do hypothesis tests about a mean, with proportions, it was always z-score, right? Because let's see if I have my test solutions for the practice test. So like the cover sheet when I look at any of the formulas that have proportions in them, the proportion is always associated with a z value, right? It's mu's that sometimes are z's and sometimes are t's. So proportion, it was nice, it was always, always z. With means, we have to decide, are we going to use z or t? Okay, so the Girls on the Run is a national program. And I guess I didn't say this in here. And I didn't say it in the program, in the paragraph. Let's say we'll say there were 1,481 girls, we'll just say from Minnesota. So Z is if we know sigma. So again, if we look at our formula sheet, anytime there's a sigma, it goes with a Z, right? Sigma Z, sigma Z, sigma Z. If we don't know sigma, if we have to use S, that always goes with T, ST, ST. Okay? So do we know the entire population standard deviation, or are we using a sample standard deviation? Right, if I'm just saying that she based her study on these girls in Minnesota, that would be a sample. Right? So we'll use T. Okay, so first I'm gonna run through how we did it before the test, basically how we did it before the test, and then I'm going to show you the quick way with the calculator, and then from now on we'll always use the quick way, but I want to show you that we'll get the same results either way. Okay, so say I was doing the classical approach, which is where I draw my graph and the rejection region. Okay, so first of all, is this a left-tailed test, a right-tailed test, or a two-tailed test? This is a right-tailed test. How much area should be in that right tail? 0.03, the level of significance. How am I going to find this value? Well, so remember we're using the t distribution, right? So if I go to my calculator, the things with t that we're allowed to use are either INVT or TCDF. Which one will we use? INVT, because we already know the area. We're trying to find the value. And so I'm going to do INVT, but remember we have to put area to the left. So what's area to the left? 1 minus that. And then degrees of freedom would be what? 1480. So about 1.88. Now what we want to do is find our test statistic. Remember, if our test statistic is in the critical region, then we reject. So our test statistic so am I going to be, say I cut my formula sheet kind of in half there. Is the formula I'm using going to be in the top half or in the bottom half? The bottom half. So which of these three am I going to use? Right, we're using the t-distribution, so it better be the one with the t, right? So x bar minus mu over s divided by square root of n. Uh-huh. Can I see? 1 minus 0.03. You did 1 minus 0.3, yeah. Okay, so the mu is the mu from the null hypothesis. So that's 2.31. What am I going to put in place of x bar? I'm sorry. Is x bar means sample average? Was that my sample average? Well, that's the assumed average. .58, right? Because afterwards we assume there was a change, right? So afterwards the mean was 2.58. And then, so when you type this in your calculator, you're going to have that in parentheses. And then divided by, and you're going to have to put the denominator in parentheses as well. So our S, what am I going to put in place of S? Yep, our N will be 1481. What's our S? 1.2. So about 8.66. So are we going to reject the null? Yeah, why? Yeah, this is in the rejection region. Or in the rejection region. Okay. So that was the old way of doing it. And I've already tested you on that. So now we're going to use the quicker way. And we should get the exact same results. The other thing, if I wanted to find the p-value, like the old way, just because I want to show you that we'll get the same thing when we do this test, if we do the p-value approach, we start at our test statistic. Like that's where we start the tail. And this is a right-tailed test. So instead of saying, okay, we need 0.03 in the test, we say we're going to start the tail at our critical value, 8.66, find the area, and then compare it to our level of significance, which is 0.03. So if I do second vars TCDF 8.66, 1 B99, 1480. I get 6.06 e to the negative 18. So again, almost a 0% chance that we would get this. So 6.06 e negative 18. Okay, so the quicker way is we're still going to hit stat, the stat button. But then at the top of the screen, we want to highlight the thing that says tests. And we are always going to use one of the following three options. 1, 2, or 5? So the z-test, the t-test, those are for means. Options 1 and 2, they're for means. And then option 5 is for proportions. And we saw in our formula sheet, proportions always go with z's. Okay. And we've already said we're using the t-distribution, so we would do option 2, the t-test. Okay, and then the very top line, the INPT, that's input. So are we going to input the individual data values, like we have all of the data and we're going to enter it into lists, or did they just give us like the summary statistics, like mean and standard deviation? And for us, they just gave us, they didn't give us a list of all of the data for every girl in the study. They just gave us the stats. And so we want to highlight stats, which I have highlighted. Oh, I was doing this on my calculator. So the mu naught, that's the naught means what's from your null hypothesis. So it was 2.31. And then our X bar was 2.58. That's our sample average. The standard deviation was 1.2. And N is 1481. And then we have to choose what type of test. So this is, we're just choosing what's in the null. Did we choose the not equal symbol, the less than symbol, or the greater than symbol? And we had the greater than symbol, so we want that highlighted. And then go down to calculate and press enter. Yes? Yeah. You want to highlight statistics on the very top row. So see, here, I said the second line is what gave us our test statistics. So see 8.66, that's what we got when we did it by hand. And the p-value is a little bit off. That's just because we did some rounding. But it's like 6 something e to the negative 18. So the 6 is in the 18th spot after the decimal, which is exactly what we got. 6 was in the 18th spot after the decimal. And then the X bar, SX, and those are already what we did. So it gave us the same test statistic and the same p-value. The only thing it won't give us is the critical value. You get it, Steve? Mm-hmm. All right. Okay, so now we're going to do an example where we have to enter data ourselves. So they don't give us just the summary. They don't just say, okay, this was our average and standard deviation. Here's the data. So, and I did this from the file that was made available to the public from Charlotte, North Carolina. So it was their traffic stop data from 2016 to 2017. And it says, according to the file, the average number of years on the service for their officers is 10.8 years. Suppose that a citizen claims that none of the officers seems to have that much experience. Based on the following random sample of 14 arrest records, does the citizen's claim seem to be a valid one? So first of all, we have to state what our null and alternative hypotheses are. So we're always going to be using either P or mu in our hypotheses. And which one is it here, P or mu? Mu, right? P is for proportion. They're not talking about proportions. We see the word average, so that's a mean. So mu equals mu something. So for the null, what should it be? Mu equals what? 10.8. So I know I'm going to have 10.8 in my alternative. Should I do less than, greater than, not equal? Yeah, because if they say they don't have that much experience, that means we think they've been on the force for less than that amount. And are we going to use Z or T for this test? T, right? Because they don't tell us the population standard deviation. Okay, so the first thing I want to do is, so in the 14 randomly selected, all of the officers happen to be male, and this was how many years they've been on the service. So what we need to do is put all of this into list 1. Is it, somehow I got 15. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, there are 15 records, not 14 records. Okay, so now do second quit, and then do stat, go over the tests, and then t-test. This time we have the data, so we want to make sure data is highlighted, not stats. And the mu, so when it says mu naught, that means the mu from the null, and that was 10.8. And my list is L1. If it doesn't already have L1 in there, then you just do second and the 1 key. Okay. Okay, hit stat. Arrow over the test. You were hitting second stat. You just have to hit plain old stat, not second stat. Yours doesn't have a frequency in it?
I figured it out.
Okay. And then we want to change it to be the less than. So arrow down to that row, highlight less than, and press enter. And then go calculate and press enter. Okay, so this is what you should do on our next test, is write down, I don't necessarily, well, yeah, it's a good idea. Actually, just write down everything that's on this screen. So I'm just gonna call it like printout. So I get mu less than 10.8, t, I'm just gonna do 2 decimal places, negative 1.12, p equals 0.139, I'll do 4 decimal places, x bar equals 9.07. And then fx equals 5.97, and n equals 15. Because if you had a typo, if all you do is put your result, and it's, say you had a typo, which means your answers aren't going to match mine, I can't give you partial credit, right? Whereas if you tell me everything that your calculator told you, then I can at least give you credit for basing your answers on what your calculator told you, and I can tell if you're making the right decision based on what's here. Right? Okay, so remember, this is our test statistic. This is our p-value. This is the sample average. So out of those 15 randomly selected traffic stop records, the average length of service was a little over 9 years. And then the standard deviation for that sample was about 6 years. Okay, so based on this, are we going to reject the null or fail to reject? Right, because the p-value, so this is saying there's about a 14% chance we'd get an average of a little over 9 years, even if the null is true, right? So since the p-value is less than alpha, right, because our p-value is 0.1399, it's less than the level of significance, which is 0.05, we fail to reject. So just because our sample average is smaller, like the claim, it's not statistically significant, right? Like if I told you, okay, I'm gonna go flip a coin in the other room and you have to guess how many heads I get. So say I flipped it 30 times and I came back and I said I got 17 heads. Would you think, oh, she cheated? Would you? No, right? I mean, you expect me to get 15, but there's like just a certain amount of variation every time I do it. I'm not going to get 15 all the time. This is a random sample. I'm not going to get the exact average every time. Every time I take a sample, I'm going to get something probably a little bit off from what the true average is. The question is it just due to chance? Like, is it surprising or not surprising? So even though you see, wow, that's almost a 2-year difference, it's not enough of a difference to be convincing, okay? So when it says, does the citizen's claim seem to be a valid one? No, there is not sufficient evidence to support the claim. That the average years on the force is less than 10.8. Oh, the p-value is, I meant to say, I said it, but I didn't write it right. It's not less than alpha, right? The p-value is greater than alpha. One last problem. And so this is from an article that just came out last week in the New York Times. And the title of the article is Why America's Black Mothers and Babies Are in a Life or Death Crisis. The article discusses many of the issues affecting infant mortality. So it says issues ranging from stress levels to differences in treatment by hospital staff when compared to white mothers. All these differences seem to have an effect on infants' birth weight. So this was, the lower birth rates were found a long time ago. I mean, like 20, 30 years ago. But at the time, people said, oh, well, it's because the mothers Black mothers are younger than white mothers on average. And so they said, okay, well, it's probably because of the young mothers. But then they found that, in fact, when you looked at teenage mothers, they had higher birth weight babies than mothers in their 20s. And so then researchers said, okay, well, stress, like the stress of dealing with discrimination and racism, is like cumulative. It builds. The longer you're alive, the more that can affect like your physiology. And so that's why even women who were having babies later had lower birth weights than teenage mothers, because they yeah, this is true. Mm-hmm.
They said that the monkeys that were older, I mean, not old, they weren't old, but they were still young, but they were older than the other young ones, had they showed their blood vessels were just almost nearly closed.
Oh.
This close to a heart attack at a young age, compare that the higher the stress level, that's why people with socioeconomic
Mm-hmm.
lower class
Yeah.
tend to usually have more issues with health, like heart disease, and die younger. Their life expectancy is like something crazy, like 12 years younger than those upper middle or the high class, upper class.
Yep. And so, they also, in this article, the article is pretty long, but it's really, really interesting. So they did, then the other thing was they thought, oh, well, it's education level. Nope. And then they found even Black women with higher education levels still there wasn't really a significant difference when they controlled, or when they looked at different groups with high education and low education. And so, like preeclampsia was actually one of the big factors that they found. It was a lot higher in the placenta separating. So it said this finding lends support to the claim that the stress of being subjected to racism and discrimination has a cumulative effect, and that the older the mother, the more stress she has endured. So this is the link, but if you just Google this, you can find the article. So it says the researchers, they have already done the study, they found it, but I was able to find data sets from the Centers for Disease Control giving birth weight data just for the Midwest from 2007 to 2016. And then I just did a random sample of 12. So the average birth weight for white babies in the Midwest during this period was 3,392 grams. So it says below are the weights of a random sample of birth weights for just 12. That was, there were huge samples, or huge numbers. So this is a pretty small sample. Born to Black mothers, test the hypothesis that babies born to Black mothers in the Midwest have lower birth weights than babies born to white mothers, and use a 0.05 level of significance. So first of all, let's state our hypotheses. So mu or p? Mu. And null has to be equals. So it would be mu equals what? 3392. We're going to assume that it should be no different for Black mothers than for white mothers. And so the alternative also has to have 3392 in there. What symbol would go in between? Less than. So if we were doing this before, is this a left-tailed test, right-tailed test, or two-tailed test? Left-tailed test. Now, the one thing I said to your calculator, this shorter way won't do for us is find the critical value. So if I ask you for the critical value in the classical approach, then you have to do that yourself. So let's just practice doing that. Oh, and this is the link to the data sets. This is the link to the article, and this is the link to the data set. Okay, so 0.05 level of significance, left-tailed test. So only one tail, we don't draw it on both sides. And what should be the area of that tail? 0.05. Are we using Z or T? T, because they don't tell us the population standard deviation. Okay. So I am going to have to do INVT. This is already area to the left, so it'd be 0.05, and then degrees of freedom, 11. So negative 1.80 or 7. So this is your critical value. If I asked you to find the critical value, this is it. Now they give us the data, so the first thing I want to do is put all of these weights into list 1. So now I'm going to go stat, arrow over to tests, and we're doing a t-test. And again, we have the data for this sample, so we want data to be highlighted. This time our mu is 3392. Our list is, I put my data into list 1, the frequency is 1, and we're again doing a less than in our null hypothesis, or I mean in our alternative hypothesis, and then highlight calculate. Okay, so the printout is mu less than 3392, t equals negative 0.495, p equals 0.3152, x bar equals 3330. If I was going to do one decimal, please. And then sx equals 434.5 and equals 12. So based on this sample of 12, again, this is a pretty small sample, would we reject the null? Why do you say yes? Okay, right. This is our test statistic. Is that in the critical region? Yeah, that's not in the critical region or the rejection region, so we failed to reject. So you might, this could open up, so a lot of times if you're actually doing statistics, this could open up a question like, was that just because I got a weird sample? Should I do it again? Should I have a bigger sample? And maybe you keep getting fail to reject. Then it might open up a question, is there a difference in the Midwest compared to other parts of the country? All right, so that's it for chapter 8. So we'll just get a tiny bit of a start on 10.2, which deals with correlation. And so here it says scatter diagrams and correlation help to determine whether one variable can help determine the value of another variable. And the two variables, so when we have two variables, they have to both be quantitative. They can't be categorical. So example there says, how well can we predict a 30-year-old male's weight if we know his height? How well could we predict an individual's income based on his or her years of education? So everything there is quantitative: height, weight, income, years of education. Everything's a number. So the response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. So the response variable is going to be like the y. We're going to have an x and a y. So the response is the y. The predictor is the x. And sometimes it really doesn't matter which one is the x and which one is the y. But if you think about income and education, which do you think you would use as the predictor? Would you use somebody's income to predict their years of education, or would you use education to predict income? Education to predict income, right? So there are some circumstances where one definitely makes more sense as the x than as the y. So it says whenever we have two variables that are both quantitative, we can think of one as an x, the other as a y, and then plot the pairs. So if it was like each man would get a dot, we'd go for the X, we'd go over to his height and then up to his weight. And there's that one man gets a dot. For a person, we'd go over to their years of education, up to whatever their salary is, that person would get a dot. So every person gets their own dot. And it says we saw examples of scatter diagrams or scatter plots in chapter 2. Okay. Definition. So it says two variables that are linearly related are said to be positively associated when above average values of one variable are associated with above average values of the other variable. So like I would think of the income education one as if there was a linear relationship, I would think that it would be positively associated. The more income, the more education, the higher your income. Not always the case, right? But in general, I would think that would be the case. I would think the same thing with height and weight. Generally, not always, but the taller a person is, the more they weigh. Okay. So two variables that are linearly related are said to be negatively associated when above average values of one variable are associated with below average values of the other. So it says when one variable increases, the other decreases. And just one example I think of quickly is like if you're running on a treadmill, if you increase your speed, the amount of time it takes you to run a mile goes down, right? So I increase my speed, my time goes down. A number called the linear correlation coefficient tells whether two variables are linear related and if they are positively or negatively associated. The correlation coefficient can take on any number between -1 and 1, but it has to be between -1 and 1. Like it could never equal 2. So kind of like probabilities can never be bigger than 1. R can never be bigger than 1, but we can also have negative values of R. Because when 1 gets big, like here the X is getting big, the Y is getting smaller, right? So we can have negative numbers for our R. And so R is just the letter they've chosen to denote the correlation coefficient. If R is equal to 1, that means the points in the scatter diagram are perfectly on a line. So R equals 1 is the best it gets. Everything is exactly on a line. If R equals -1, they're still perfectly on a line. It's just, it goes downhill instead, but it's still perfect. So the worst case scenario is 0. There's no relationship at all. Then they're just all over the place. It's just random. And so here are some like illustrations of different values of the correlation coefficient. So if R is 0.851, first of all, that's positive. So that means like if you look at the cloud of dots, they should generally be sloping uphill. And you can sort of see that. And the closer it is to 1, the more tightly the dots are sent, like just about a line. So the farther it gets away from 1, the farther the dots kind of spread out. And so B, -0.965. So see, these dots are clumped together more closely about a line. It's downhill, so it's negative. But they're closer to fitting on a line than in the first graph, so it's closer to the -1 than this is to +1. And then here's R equals 0, they're just all over the place. Now this one, you can see there's a perfect like pattern to that line, but it's, a perfect pattern to those dots, it's just not a line, right? So there is a relationship, but it's not linear. This R only measures how close they are to a line, not how close they are to a pattern, only to a line. So even though there's a pretty distinct relationship, it's not linear, so the correlation coefficient is not very close to 1. We'll do page 2 on Wednesday. the table, it's the very last page of our notes. There's table A6. So it says critical values of the Pearson correlation coefficient are. And so this is at the 0.05 level of significance, the 0.01 level of significance. And so this N is the number of the number of dots, which will also be like rows in the table. Like how many individuals you have data for. It's like your sample size, right? And these values right here, so it's like your H naught is, there's no relationship between the variables. There's no relationship between X and Y. Which would mean like your R equals 0. It's just random. And so you see the note, it's just like with hypothesis tests, they always use Greek letters. So we had mu or P. Here they're using a rho. It looks like a P, right? But it's a rho, which is the Greek letter. That's the equivalent of R. And then H1 would just be, there is a relationship. Oops, there is a relationship. Which means R is not 0. And this is saying R has to be at least this big to give sufficient evidence for the alternative. Okay, so we'll see more of that on Wednesday. We're just going to answer this question right here, and then I'll have you do group work. So this says, could we calculate a correlation coefficient if we wanted to say investigate a link between a defendant's race and ethnicity and the length of their jail sentence if they were convicted of a crime? Could we? What kinds of variables do we need? They have to both be quantitative. Are both of these quantitative? No. This race ethnicity is not quantitative. The length of a jail sentence, that would be quantitative, but this is not quantitative. So not that we can't do like hypothesis tests about it, but we can't find a correlation coefficient. All right.